most hydrocarbons that are just hydrocarbons are not soluble in water. Everybody knows that oil and water don't mix well. One word that's used to describe the hydrocarbons that would be considered oil, petroleum products, is hydrophobic. It hates water, water hating. Whereas the sugar would be considered hydrophilic, water loving. The alcohol would be considered hydrophilic because it loves water. So the oil hates water. This is just a picture of oil on top of water, and it's because you know, with the water itself within its own liquid, you know, has all these strong hydrogen bonds within a sample of water. Obviously, the water is held together in a liquid. We've talked about this for all the hydrogen bonds. Now, whenever, you know, water pulls something into solution, then these bonds are going to be sort of disrupted, and the water is going to make new attractions with, in the case of the ionic compounds, with the ions, or in the case of polar molecules, with other the ends of the more polar ends, the positive or negative ends of the polar molecules. Now with oil, so oil would just be these long hydrocarbon chains that we abbreviate this way. This would be carbon, 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 carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This would be like Dodecane, an example of a hydrocarbon that you might find in oil. Dodecane, it'd be an oily kind of consistency. Those molecules, of course, are all held together with all of these dispersion forces, right? Holding them all together. So they're nicely held together with dispersion forces. So there's no reason for the dispersion forces to be disrupted by all of these OHs, because it's just such a large, you know, sampling of the what do you call it, dispersion forces holding this together. So it would all be surrounded, each molecule surrounded by another water hating molecule, and it would stay together, and there's no reason for this to separate. Now if you mixed it really well, you might be able to get some waters to induce some dipole moments and get a little bit of the oil mixed in, but as it is, you know, it's going to then quickly collect back together because it hates water. All right, so that's why we have layering when we mix, for example, oil and water. Okay, now what about oxygen and water? Oxygen is a small non-polar molecule, much smaller, you know, than oil would be, and oxygen exists, you know, at normal temperatures and pressures as a gas. And so what happens, does oxygen dissolve in water, non-polar gas? Well, obviously, in order to sustain you know, fish and plants that live in the water, oxygen has to dissolve in water to a certain extent. And so that would be an example of a dipole, induced dipole type of an interaction, where a small nonpolar molecule, a small nonpolar molecule that only has induced dipole type of dipoles could interact with a polar molecule, such as water. So the oxygen would temporarily, a dipole moment would be induced in the oxygen by the water molecules. So there's obviously a lot more water. The oxygen itself wouldn't already be grouped together like oil is because it's a gas. So the individual oxygen molecules, as they're bubbled into water, or as they exist at the interface of a water and collide and move into water, don't have each other to clump together with. So they would be surrounded by water, and then the positive end of the water could induce, you know, the electron cloud to move and induce a temporary dipole moment where you have a negative end and a positive end coming and going and coming and going, and that's how we hold oxygen in water, with this dipole, induced dipole type of interaction. So it can happen, obviously it does. It's just low solubility. It takes a lot of water to hold a little bit of oxygen in, and there's a lot of factors that affect it. So the concept here is like dissolves like, and the more unlike the molecules are, the less likely or the more difficult it is for them to dissolve each other.